All right, in this video, we're going to be working BC Homework 11.3a, doing some more series practice, this time with alternating series. So you heard in class about the alternating series test. If you've got a series whose terms are alternating, their size is decreasing, and their limit is 0, then you've got a convergent series. Okay, so the first problem says, use the alternating series test to show that S converges. Okay, so I'm going to say, okay, well, first S is alternating. And because it's the first problem, I'd say I know that. Whoops. Because of that, -1 to the n. Okay, the second thing is that the magnitude of the terms is decreasing, so that's going to be, okay, the absolute value, you're going to have to take the absolute value, -1 to the n over n squared plus 1 is decreasing. Yeah, because the bigger n gets, the bigger the denominator gets. Numerator stays either 1 or -1, but then take the absolute value of it. So absolute value is decreasing, and the limit of the terms is 0. Okay, so limit of infinity of -1 to the n over n squared plus 1 does equal 0. Okay, so that's the alternating series test, so that means, S converges. Alternatively, we do have the option of just writing the one sentence, if we remember the words right, and I've got it just ready here. S is alternating with terms that decrease in magnitude to 0, and there I wrote it in, and there you go. That's also an option for how you can use the alternating series test. I'll probably just be using the sentence because I've got it on the clipboard ready to write. I might write a little bit too, but use the first 4 terms of the series to approximate the value of S. So I'm going to say S is approximately equal to n equals 1. That would be -1 to the first over 1 squared plus 1. -1 to the 2 over 2 squared plus 1. -1 to the 3 over 10. And -1 to the 4 over 17. All right, now we do not need to go and find a common denominator for that. I think it's going to be 170. Yeah, because 17 is a prime number. So, yeah, all of that, I don't really need to do that. What is the maximum possible error in the approximation for S using the first 4 terms? Okay, now what you can do is, we've already verified that S is a converging alternating series, so we can use the error bound. We can just say error less than or equal to the absolute value of the next term, which would be, let's see, we did up to n equals 4, so n equals 5, -1 to the 5. You can even just -1 to the 5 over 5 squared plus 1 is 26. Okay, that's going to be our error bound, 1 over 26. But if we thought about, like the terms of S at the start, if I had this do over again, I might just like kind of write out the terms from the beginning. So that's -1 over 2 plus 1 over 5 minus 1 over 10 plus 1 over 17. I determined that the next one was going to be -1 over 26. Will the next denominator be 37? So plus 1 over 37 minus, okay, keep going. And we could have seen that, had we stopped at 1 over 17, the next term's absolute value is our error bound. So that's that 1 over 26. All right. And how many terms would be required to approximate S with error less than 1 over 70? Well, let's just keep this pattern going. But maybe I'll grab this and bring it on down. Alright, so the next one would be 7 squared is 49, so 1 over 50 plus 1 over 8 squared plus 1, 65. Is 1 over 9 squared plus 1. There we go. All right, so that's finally less than 1 over 70. All right, so if I want that 1 over 82 to be the error term, I'm just going to say I'm going to stop here at 1 over 65, and that would be 1, 2, 3, 4, 5, 6, 7, 8 terms. Now, if we needed to solve this one algebraically, I've never really liked the way I solve these. I've never really come up with a better way. But it says error is less than 1 over 70. So we're going to look for, kind of a situation where our error bound first goes underneath 1 over 70. So I'm going to say error bound equals the absolute value of the next term, an plus 1. And we need that to be less than 1 over 70. Then I'm going to say, okay, well, I can plug n plus 1 in for right there and right in the formula for S. Or really, I guess that's showing me the formula for AN. And that's going to be 1 over n plus 1 squared plus another 1. So, okay, and then with this, a situation like this, I don't really recommend like cross multiplying or anything like that. I think you're just gonna be better off thinking about, okay, if n goes like higher than some number, then I'll have this inequality be true, right? Because a bigger n is going to give a bigger denominator, lower fraction. And I think about if n equals 7, I had 8 squared plus 1. That was not, no, wait, 8, 64. Yeah, no, that was not right. I needed 9 squared plus 1. So in that case, n equaled 8, and that's how I knew I needed 8 terms. Okay, so I don't love that, but I'm sure there's a better way out there. I think the best way is to just like kind of have a hypothesis and then check it by, making the error bound again. So then what values of p make the series converge? Okay, the first one's geometric. We know that geometric series, we need that ratio to be between -1 and 1. So that's going to be p between -2 and 2. This is a p series, and so that's going to be where we need that power, that exponent of n to be greater than 1, and that's going to be where p is greater than 2. Then this other one over here, this is an alternating series. So as long as that power works in such a way that n stays in the denominator, I'm going to have convergence by the alternating series test, because if I have any positive power of n in the denominator, I'll have terms that are alternating, decreasing in magnitude, and going to 0. So I'm thinking p plus 2 needs to be greater than not or equal. If it was equal to 0, I would not, I'd just have the sum of -1 to the n, and that's a divergent series. Okay, so to make it converge, I need this greater than 0, so that's going to be p greater than -2. Right. Then number 8, okay, yeah, because we have not talked that much about factorial in this class, I thought it might be good for us to just go and like get a reminder that, something like 3 factorial is 3 times 2 times 1, so that's 6. Okay, 2 factorial is 2, 1 factorial is 1, that's not hard. 4 factorial is going to be 6 times 4, and 5 factorial would be 120, or yeah, it's 120, because it's 24 times 5. That's 100. 20 times 5 plus 4 times 5 is 120. 6 factorial is 720. And I would say 7 factorial is greater than 1,000. Okay, now 0 factorial, that's another number we need to know. It's not going to be the most important. Actually, I guess it is right here on number 9. So yeah, I guess that's just so nobody's surprised, the 0 factorial is going to be 1. And if you need further discussion on factorial or why 0 factorial is equal to 1, just come talk to me. I'd be happy to explain it to you. So does f of -1 converge or diverge? Justify your answer. Okay, well, I'm going to first kind of like write out what's going on with f of -1. That's the sum as n runs from 0 to infinity of -1 to the n over n factorial. Now notice that bigger n gets you bigger factorial. We're seeing that across the top. So if I've got n factorial in the denominator, the magnitude of the terms is decreasing and their limit is going to be 0. Because there's no upper limit for factorial. So this is an alternating series that meets all the conditions, so I'm going to say this is that not fitting. Okay, all right, well. Okay, so that gives me convergence of f of negative 1. Where we can only use the alternating series test to show convergence of a series. If f of negative 1 was going to diverge, we would be able to see that by the nth term test. Okay, use the first 4 terms of the series to approximate f of negative 1/2. All right, well, what I'm going to do, I'm going to actually write out some more terms. X to the 2 over 2 factorial, x to the 3 over 3 factorial, because I have a feeling we might need do an error-bound type problem in the future. So f of negative 1/2. Right. F of negative 1/2 is approximately equal to 1 plus negative 1/2 plus negative 1/2 squared over 2 factorial. First 4 terms of the series, so plus negative 1/2 cubed is going to be negative 1/8 over 3 factorial. Okay, so that's, I'm not going to put it to plus dot 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 because I'm just only using the first 4 terms to approximate. Right, and then on number 11, show that the true value of f of negative 1/2 differs from our approximation by an amount less than 1 over 200. We've already verified the convergence of the series by using the alternating series test. We've done all the conditions. So we're going to say for alternating series error bound, error is less than or equal to. We always start off like that. And then, okay, we're going to say the next term would have been the one with 4 factorial. So negative 1/2 to the 4th over 4 factorial. And then by an amount less than 1 over 200. Here's the thing. We're just going to say that this is less than 1 over 200 because either we have done the problem right and we have justified our answer properly with what we've written, or we haven't, right? And with the error bound I've got, it either is or is not less than 1 over 200. I do not personally believe that it's worth your time on free response questions like this to go in and verify the arithmetic. I'd say just trust yourself and either be right or be wrong. Now, I will show you how this is going to be an amount less than 1 over 200 because it's always there for you to see in the arithmetic, but you don't need to or probably want to write this out on, on your actual free response paper. So, negative 1/2 to the 4 is 1 over 16 times 1 over 4 factorial is 1 over 24. Okay, 16 times 24 is definitely going to be bigger than 10 times 20, which would be 200. So I can say that this is definitely less than 1 over 200. All right, and then this backwards kind of question here. How within 0.001 of its true value? To estimate. Okay, this is the rough draft of the homework. Within 0.001. All right, so I'm going to need to write out some terms, or do I? Okay, no. I can just see, okay, when is the next term absolute value less than 1 over 1,000? So that's kind of a question of when does n factorial go greater than 1,000? And I wrote that down right up here. That was a 7 factorial is the first one that goes greater than 1,000. I knew that was going to be important. I just couldn't remember why. Okay, so I would need 6 terms, so that the error is the 7th term, which is 1 over 7 factorial. Okay, so 6 terms. All right. Explain why the alternating series test cannot be used on the series. Okay, so the alternating series test, we need, actually write these conditions out. Alternating decreasing in magnitude I'm just going to have to say size and have limit 0. So all of these are going to be missing at least one of those. Okay, number 12. This one is not alternating. if I've got negative 1 to the n and cosine of pi n, I believe, let me just start off, n equals 1. I have a negative 1 here, a cosine of 1 pi is also a negative 1 divided by 1 factorial. Plus, when n equals 2, I'm going to have negative 1 squared is positive 1. Cosine of 2 pi is positive 1. And see, it's always going to either be negative negative or positive positive. And this thing is not alternating. All right, 1 minus a fourth plus a third minus a 16th plus a fifth minus a 36th. I see the pattern. The even terms are squared and the odd terms are just like the harmonic series terms. Okay, these terms are alternating. They are going to 0, but they are not uniformly decreasing in magnitude. So I'm just going to say terms are not decreasing in magnitude. Now, number 14, this series is diverging. Okay, I'm noticing this because the degree on the top and the bottom are the same. The terms aren't even approaching 0, so how could it even come close to converging? So I'm going to say, I'm going to actually say, I'm going to use the nth term test on this one. The limit as n approaches infinity of negative 1 to the n. The limit of the fraction's 2, but the limit of the terms doesn't exist because it's going to bounce back and forth between stuff really close to 2 and stuff really close to negative 2. Okay, that does not exist, meaning the series diverges. And that's a good reason why we can't use the alternating series test on that series, because the alternating series test only shows convergence, can't show divergence. Can't really use it on a divergent series. Same thing here. We know this one. This thing diverges. It's alternating, but the terms are not decreasing in magnitude, nor are they going to 0. But I would say this series diverges, and that's the best reason. Okay, and in case you didn't remember from any of the other times we've dealt with this series, this thing diverges because the limit of its terms is not equal to 0, right? The limit of the terms doesn't exist at all, so that's what I'm going to say. If the limit of the terms does not exist, the limit of the total has no chance of existing either. All right. And okay, so then here is the last set of questions. What is f of 0? Okay, so if we plug in, actually let me write out some terms here because this guy kind of got a lot going on. Negative 1 to the n plus 1, so we start at n equals 1, negative 1 to the 2 is positive 1, x to the 0 is 1 over 1 times 2 to the first, so that's 1 over 2, plus, probably going to be a minus, looks like it's going to be an alternating series, x to the 2 minus 1 divided by n equals 2, 2 times 4 is 8. I'm going to actually... I think it would be best for me to write it like this. X squared over 3 times 2 to the 3. Yeah, I like this better. Minus x to the 3 over 4 times 2 to the 4, and so on. Okay. F of 0, think about what happens if I plug in 0 in for all of these x's right here. I'm going to get a whole bunch of zeros. All the rest of these are going to have higher and higher powers of x. So I'm going to have a whole bunch of zeros, and this series is going to converge to 1/2. So f of 0 equals 1/2. Use the first three non-zero terms of the series to approximate f of 1. Okay, well, f of 1 is going to be approximately equal to 1/2 minus 1 over 2 times 4 is 8, plus 1 squared is still going to be 1 over 3 times 8 is 24. Okay, and I might say I'd say it's 12 24ths minus 3 is 9 24ths plus 1 would be 10 over 24, all right, if we needed to. Alright, show that the approximation from B differs from the true value of f of 1 by an amount less than 1 over 50. This is another one of those where they're going to kind of tell us that we're trying to show it's less than 1 over 50. We're going to take that largely on faith. But first we're going to say f of 1 is an alternating series. Yeah, we can see that, whose terms are clearly decreasing in magnitude and going towards 0, yeah. Wow, that's okay. That wasn't as bad as I thought. An alternating series whose terms decrease in magnitude to 0. Okay, which means it converges, and I can use the alternating series error bound, which is going to be the first neglected term. So I went up to 1 over 24, which was this term right there. So the next term will be my error bound. And I'm going to say error less than or equal to, because we always start these error problems, absolute value of negative of 1 to the third divided by 4 times 2 to the 4 is 16. So that's 1 over 64, which is less than 1 over 50. Okay, now I would be honest, I don't even recommend doing that. I might just say we'd be best off just writing it out and saying, hey, that's less than 150, because either we're right or we're wrong, and there's not really any added benefit to doing that computation there. All we can really serve to do is confuse ourselves, or, you know, if we're really having doubt about do we do it the right way, we can go in and check that arithmetic. I think I don't want to lose sight of that. What's the least number of terms required to get an approximation within 0.01? Well, 0.01 is 1 over 100. And so I'm really looking for, when does the next term go less than 1 over 100? All right, I don't think that n 2 to the n equals 100 is an equation we're necessarily trying to solve by hand. So I'm just going to say 1/2, yeah, minus an 1/8 plus a 24th minus 1 over 64. I have to imagine the next term is going to be less than 1 over 100. What happens at n equals 5? So negative 1 to the 6th, x to the 4th, well, it's going to be 1 to the 4th, which is 1. 5 times 2 to the 5. Yeah, there we go. 5 times 32 is feeling like 160 to me, but that's definitely less than 1 over 100. So if I used 4 terms, then the 5th term would be the error bound. Yeah. Okay, 4 terms there. Because if I stopped after n equals 4, then the 5th term is the error bound. That's that amount that would be less than 1 over 100. All right, and then number 20, let g equal the integral from 0 to x of f of t dt. This is really the type of problem we're going to see in the next unit more, but I thought now would be a good time to do that also, because you don't need to just go and do alternating series test 100 times the same way you need to do limit comparison test a bunch. The first 3 non-zero terms and the general term for g of x. All right, so what I'm going to do is I'm going to kind of copy in f of x. It's equal to 1/2 minus 1/8 of x plus, I'm going to write it kind of more like a polynomial, 1 over 24, so it went 8, 24, 64, first 3 non-zero terms. All right, that should be good enough. All right, plus 1 over 24x squared, all right, minus ... Okay, because if I do that, that'll be enough to give me 3 non-zero terms of the antiderivative. Now, what you're going to learn in the next unit is that we can just antidifferentiate f term by term, figure that c is going to equal 0, and kind of call it a day. But if you're having any doubt about this, what I'm going to do, I'm going to take it step by step. I'm going to replace all the x's with t's. You see, it's no different. And then when I go to integrate from 0 to x of f of t dt, that's going to be the integral from 0 to x of 1/2 minus 1/8 of t plus 1/24 of t squared minus dt. Okay, now sometimes what we can do is we can just like get the first three non-zero terms and we can see the pattern. And sometimes we're going to want to antidifferentiate the general term. But I think this is one we're going to want to just see the pattern. All right, so if I antidifferentiate, I'm going to get 1/2 t minus 1/16 t squared plus 1/24 times 3 is 72, t to the third minus ... as t goes from 0 up to x. And when I plug in t equals 0, I'm going to get all zeros, right? Because the other terms are just higher and higher powers of t. And when I plug in x, I'm just going to kind of undo what I'd done before, and that's why I'm able to just antidifferentiate term by term. Minus 1/16x squared plus 1/, I can't figure out the pattern with the numbers though, x to the third minus ... It said the first three terms and the general term. So I'm going to go back over here to the general term and kind of try to take the antiderivative. And you might be thinking like, oh goodness, that looks like much harder than any antiderivative we've needed to take. But in reality, all of the stuff that isn't x is just a number, right? It's different numbers. But for a given value of n, it's just a number, and all those things are constants, so it's really, what I do is kind of get rid of some of this work over here. I don't think we need that anymore. Let's say this is really the sum in going from 0 to infinity of -1 to the n plus 1 over n times 2 to the n, I see it now, times x to the n minus 1. And when I look at it like that, I think it's a little easier to see. What I do when I antidifferentiate is I add 1 to the power of x, and I divide by the new power. Okay, so I'm going to have an n, but I still have the n times 2 to the n and the -1 to the n plus 1, because the antiderivative of, say, 5x is going to be 5x divided by 2 to deal with power rule. That 5 still stayed there. All right, so all of that, I'm going to have n squared 2 to the n. All right, so n squared 2 to the n, -1 to the n plus 1 times x to the n plus ... All right, and oh, you can barely even see that. Okay, there it is. But that's all for this homework, so that's all for this video. Thanks for watching.